Okay, hi everyone. Today we will be presenting our mini drone final design presentation. We are from CalSat LA, the College of Engineering, Computer Science, and Technology. Our client is MathWorks. Our team name is the Golden Knight Eagles. Our advisor's name is Michael Thorburn. Our team members are Miguel, Lester, Gina, and me, Luis. Next slide. So today we will be talking about backgrounds, objectives, requirements, work breakdown structure, CAD transfers and findings, the grabber itself, image processing, state flow, magnetic control, hardware tuning, and at the end we will have simulation versus real life videos. Next slide. So for the background, MathWorks is a company that specializes in computer language for technical computation. The MATLAB program is used for data visualization, data analysis, programming, computation, and much more. The MathWorks competition, student competition, was created to enhance creativity, teamwork, and multiple possibilities for industry experience. And on the right, you will see the two things that were given to us, which is the hardware support package in the middle picture, and on the bottom, the drone. Next slide. So for our objective, we were tasked to modify a drone to be able to follow a designated path and detect an object. The pictures you see on the bottom is the drone, the path, and the two objects that we will be detecting today that we will talk about more thoroughly later. Next slide. So for the requirements, we had two sets of requirements that were very similar. We had the MathWorks competition and our senior design requirements. So for the MathWorks competition is to be able to detect a red guided path on the ground, be able to safely fly through that path, be able to withstand disturbances like wind, and at the end of the path, just be able to land on the landing pad. Now for senior design, we had the same ones, except that towards the end of the path, we had to be able to get the drone to hover down and pick up a Rubiks Cube. And be able to fly back up with the Rubiks Cube safely and be able to go back to the beginning of the path. Now, I should point out, this is not a 3x3 inch Rubiks Cube. This is the mini Rubiks Cube, the one that you see on the top right picture there. Okay, next slide. So for our work breakdown structure, I had to do 3D world editor research, a 3D Solidworks model, transfer the SolidWorks model to the virtual world, and do virtual world editing.
For myself, my work breakdown, my task was to finish all parts of the grabber and that loads and was distributed, and finally send the file to be 3D printed, along with importing it into the 3D world editor and making an assembly with the drone and the grabber.
So for my part, I had to hover tuning, threshold tuning, following path tuning, and aligning tuning.
So I'm Miguel, and I worked on the Simulink state flow charts, the image processing, the manual control for the drone, and tuning the controllers.
Okay, so for the CAD transferring research, this was mostly done with the MathWorks documentation that's provided on the MathWorks website. This also includes video examples and just other examples that they already have on the website. What I found best for the 3D world editor that you see on the top right, on the picture on the right, that it's better to transfer STL files for the 3D world editor for virtual simulation. And as for the XML files, that is also an option there. It works, but it's better to use that for SimScape. And you can either import this as a child or as a root in the 3D world editor. Next slide. So the first model that I transferred was a Rubiks Cube. First, I had a full assembly of a fully made Rubiks Cube with the internal parts and bolts, but that would have taken too long to have, I guess, meshed together and working in the 3D world editor. So therefore, I just made a single part, and when it imports, it imports as a default part, but it can still be edited, as you can see right here on the top right. That is the color that we chose to go with for computer vision and be able to do the image processing. Next slide. So the second model that I transferred was the drone. The drone was the, sorry about that. It was the grabber that the drone comes with. So this grabber here that you see on the top right, that is the one that the drone comes with, and the bottom ones is the one that I did on SolidWorks to transfer to the 3D World Editor to be able to do it for practice, but we didn't just want to do it like that. We wanted to make our own. Next slide. So for my findings for the simulation, when I imported the grabber into the 3D World Editor, I found that we could not simulate grabbing movement in the virtual world. When I asked the MathWorks engineers, we were advised to use Simscape, and we didn't want to use Simscape. We wanted to do, we wanted the drone to do it autonomously in the virtual world. So like that, when we upload it to the drone, it would do it autonomously. Since we couldn't do it autonomously, we switched to manually. And my teammates will talk about that in the future. Right. Next slide. I will now pass it on to Gina.
Hello, my name is Gina. So designers such as our team were tasked to use our creativity to design a pickup mechanism to be able to pick up a Rubiks Cube. Preliminary design included producing requirements to follow and develop a product that will work efficiently and following SME standards. Some requirements include, just to name a few, the grabber must be able to open and close. The grabber must pick up a 13.6 grams Rubik's Cube with dimensions of 1.05 inches each side with a volume of 1.16 inches cubic inches. The design must not be able to counteract with the support systems such as the camera inside and control systems or any sensors inside the drone. It must not have any sharp edges for safety. On the right, as you can see, we have a table of concept decision matrix, which was color coded. The table was colors. The color schematic represents the blue for best, the green for good, yellow for same, and red for worst. Initially, we picked the design number 2, but we reverted back to our second choice, which was concept number 1. Next slide, please. Parts list. This table includes my progress of the parts modeled for the grabber carefully distributed throughout the semester to meet deadline. On the table, I have the part number along with the part name and the file name, which I saved it on. The material applied, which was the ABS plastic that's going to be used when it's 3D printed, and manufacturing is done at the Costello makerspace, also with the final checks for all the designs. Next slide, please. The grabber design I have is for the first concept choice, which is assembly 1A. That was the first initial grabber design with a lot of parts. It had a downside, making it heavy. It was not up to scale, and it had a lot of surface area. For the second one, assembly 1B, that was the final design we went with. It was up to scale. It has less surface area, and it was much lighter. Next slide, please. FEA, which is finite element analysis, this shows the max load it's required until it deforms. The same was done for all the parts that have load applied to them. This analysis is done because we can we can see when the material starts to deform in a plastic-like fashion. The results on the load applied, the load that was applied to it was 13.6 grams, which is the weight of the cube. The yield strength was 4.7 times 10 to the 7th power. As you can see to the right, it is all the way to the yellow. It is close to the red, which means that it fails at that color. But since everything was below, the yield strength was below, that means that our part passes the test. Next slide, please. FEA and factor and safety distribution. The safety factor table includes materials, which was the ABS plastic. And to the right of the table is the factor and safety distribution with a min of 77.003 and max of 1000. This is defined as the ratio between the strength of the material and the maximum stress of the part. The equation below, which is sigma von Mises over sigma limit, simply means the stress max is greater than the strength. It means it will fail. But as you can see, it is less than 1. That means that any part that is anything below 1 will fail. Since our min was at 77, that means our part passed the test. Next slide, please. The drone. We used the CAD of the Parrot Mini drone competition. As you can see on the right, the drone was scaled down to parts. It had no part details. And the drone was also scaled up to meet with the approximate grabber dimension, which we had a problem because as I transferred the drone to the assembly, it gave me a wired pattern and it could not be scaled up to the same scale as the grabber dimensions. So we have yet to solve that solution. Now I'm gonna pass you to Lester.
Okay, so we used image processing. So there were 2 different methods that were applied to this image processing that we used. One was hue transform, which is, it was used mostly to find the line angles from the track that it would see on the bottom to help the drone be able to generate its flight path. We also used counting the number of pixels in the area, which was used at the end of the track. So when the drone got to the very end, it would find the landing pad and it would count how many pixels were in that, and then it would be able to safely land inside the pad. Both of these methods used image threshold. Next slide, please. So image threshold was a tool that we were able to use to help us isolate the colors that we did not need. So as you can see in the bottom right corner, you can see what the drone is actually seeing. But on the left side is what the drone was actually seeing because of what we configured it to. And then this helped the drone be able to find the track and then be able to travel through the path. Now passing it to Miguel.
So here we can see the state flow charts used for the navigation along the path. And it could really be broken down into a general 4 blocks. The start block, which sets the initial position. And then we have the path following block, which identifies the line angles, the line position, and determines if there's a left turn or right turn ahead. The next block is the landing block, which enables landing and begins searching for the landing pad, whether it has to move left, right, or forward. the next one was the object pickup, which was not tested on the hardware drone, but was working fine in simulation, which locates the object autonomously and hovers down to it. Here we have the landing section or the landing procedure. What happens here is we take the image from the drone and we split it into 3 different matrices using the submatrix block within Simulink. And it's split up into the top left, the top right, and the center of the image. We take the difference of the top left and top right to determine if the landing pad is to the left or to the right of the drone. And then the center matrix is used to identify if the cube is directly below the drone yet. And once there is more than 150 white pixels below the drone, it will switch on the landing procedure and begin its descent. Here we have the manual control. And what we did here was we used the keyboard read block, which was part of the Parrot Mini drone package within Simulink, which allows us to map different keys from the keyboard and set them up to control different movements for the drone. As you can see in the state flow, we have, for example, we use the WASD keys to control left, right, forward, and back. And then we use the IJKL keys to control moving up, down, and the yaw.
Okay, so the controls tuning. So the system had 4 separate controllers, the yaw PD, XY to reference PD, attitude PID, and the total thrust PID. So what we basically used the most was the attitude and the XY to reference. So what you can see in the bottom is a PID chart that was a guide for us to help change the P, the I, the D. So after hundreds and hundreds of combinations, we use this to help us implement what we wanted the drone to do. Next slide. So here's the hovering attitude controller. So in simulation, the PID values were perfectly fine. The drone functioned properly. Once we uploaded it to the hard drive, the drone would basically crash into the wall. It wouldn't even go up. The values weren't working as we expected. So in this table, what we did is we did hundreds and hundreds of different combinations with the PID controller table. And we basically wrote down some of the values that basically gave us the closest amount of, near perfect, but we still need more work. What we noticed was that as you changed the numbers, they were very small numbers. It was probably around 10% difference, but changing one of these numbers actually changed the way the drone would fly drastically. It would either pitch or it would roll too much or so on. And then what this basically turned into a trial and error. So what we would do is we would try to plug in numbers and try to see what way the drone would go. And then we would either increase the numbers or decrease the numbers until we actually got the drone to stabilize and do what we wanted to do with minimal errors. Passing it to Miguel.
Okay, so here we can see the controller used for the XY to reference orientation. This controller's main job is to convert the X and Y commands into pitch and row commands. So essentially what it does is it'll take the estimated X and Y position and the desired X and Y position to determine how much change is needed and provide the row and pitch accordingly. In this next slide, these are our plans for once the claw is attached to the drone. We anticipate that the claw would add a significant amount of weight to the drone, and we'll probably have to retune the controllers to account for this, and we will probably also have to adjust the power distribution between the motors, as you can see in the red box. So currently, all motors receive the same amount of power gain, but most likely two of the rear motors would have to get an increase of power to handle the extra weight. And here we have a video recording of the simulation recorded on Simulink and the flight visualization. So here, what we see now is a wind simulation. So although the drone was blown off of the track, it was able to regain its position and follow the track. And we see that it's able to handle right turns, left turns. And there it is able to find the cube, move to it and lower down. Now it's going to turn around and make its way back to the beginning. So again, it follows the track, it makes its turns, and all of this is done autonomously by calculating the line angles using the hue transform. Once it reaches the end, it'll do the second version of image processing we have, which was counting pixels. So it'll be moving left and right and then forward and eventually land. And that is pretty much everything we were able to successfully simulate. And we're hoping to be able to accomplish on the hardware drone.
So as the drone flew near perfect in simulation, once we uploaded to the hard drive, the drone really wasn't able to do everything we wanted it to do. So what we did is we tested the blocks individually to see if they would work. We just need more testing for all the blocks to work perfectly. So here we actually have a video of the drone flying, following the path. So as you can see, we press start. This is a track we built at home. And what the drone does is it finds the track on the bottom. And then once it finds the lines, it generates to go forward. And as you can see here on the laptop right now, you can see what the drone actually saw. So it saw the track, and then as soon as it saw it, it processed to move forward. So next video. So here is another test that we did where the drone aligned itself. So as soon as we start, the drone starts to generate and it starts to hover. It takes usually around 10 seconds to go to the next block. And then once it does that, it sees the bottom, it sees the track. And then once it does that, it turns and it aligns itself. And there you can see what the drone saw. And basically we still have more testing to do, but this is what we were able to do on the hard drive.
That is all we have for today. Any questions that you may have after watching the video, you can definitely write down and we can answer those during the executive summary presentation at the Senior Design Expo on May 2nd. Thanks for watching.
Thank you.
Thank you.